This is lecture 24. In this, so we start with a simple proposition, which we had sort of discussed earlier. I just want to clarify it, sort of discuss that in a minute. Okay. So, R Noetherian, N inside M finitely generated R modules. Okay. If N is P primary, so P is a prime ideal, P primary, then the annihilator of the radical is P. Okay. This we saw earlier. Okay. Now this is not, it's not true that any ideal with a radical P. So what does it say for ideals? So let's, okay. For ideals it says that if I is a P primary ideal, so it means that P primary submodule of R, then the radical of the annihilator in R of R mod I is P. This is what it says. But what is the annihilator of R mod I? So just this itself, this is just I. Okay. So in other words, that is radical of I is P. This is what we have. Now, this is so, okay. However, in general, there are ideals. In Noetherian rings itself, I such that radical of I is a prime ideal, but P is not, but I is not P primary. Okay, let's look at an example. Let R be the polynomial ring in two variables over a field K. Now let I be the ideal generated by x squared and xy. Okay. What is the radical of I? The radical of I? Well, x must belong to the radical of I, because x square is inside I. But if x is in the radical of I, then xy is automatically there. Okay, so this implies that xy, okay, so x is inside here, and this now implies that radical of I is the ideal generated by x, and R modulo the ideal generated by x is isomorphic to ky, which is a domain. Okay, so therefore, radical of I is a prime ideal. Okay. However, a prime ideal X. However, I is not X primary. And why is that? So consider what is the annihilator of x bar inside. So let in the module R mod I, the annihilator of x bar annihilator in R of the element x bar is the ideal generated by x and y, since x bar square equals 0 equals y bar square, sorry, not y bar square, y bar x bar, sorry, this is, one is x, the other one is y, yeah. X bar, y bar, okay, so this, okay, and x bar, y bar, annihilator in x is, sorry, there is no x here, x, y, this is, okay, and xy is a maximal ideal of R. So annihilator contains this maximal ideal, but it doesn't contain 1, so it must be equal to the maximal ideal. Okay, so therefore xy is associated to R mod I. Okay, and of course the minimal prime x is also associated to R mod I. So there are two distinct primes, so therefore I is not x primary. Okay. So in general there are radical ideals there are ideals with whose radical is a prime ideal, but the ideal itself is not primary. And in fact the ideal x square y can be decomposed into irreducibles as x, sorry, not x square y, xy can be decomposed into irreducibles as x intersect x squared y. So here it says it must be, so one can check that this is equal. Okay. This is clearly the right side contains the left side, and right side contains the left side. On the other hand, if you have something on the right side, it must be divisible by x, and it should be divisible. It is written as a linear combination of x squared and y, R linear combination of x squared and y. And then you can remove the x terms outside and show that there must be an xy term. Okay, so this is equal, and both of these. So this is prime. Both of this is prime. So primary, okay, and also irreducible. I mean, all of the thing that we want. This is irreducible. Okay, this is exercise. Okay, so here is a decomposition into an irreducible decomposition with two distinct associated primes. The associated prime of this is x. The associated prime of this is xy. Distinct associated primes. So this cannot be a. This is the irreducible decomposition of x square y, x square comma xy. However, we have the following proposition: R Noetherian. Okay, M maximal ideal, not necessarily unique maximal ideal. I an R ideal such that radical of I is M. Then I is M primary. So quite often, at least in the context of Noetherian rings and M a maximal ideal, quite often people will interchange these two terminology, just say let I be an M primary ideal and write that, or write that and say M primary. Okay. So one should, that these are equivalent notions for ideals whose radical is a maximal ideal. Okay. So proof. Okay. Consider the support of R mod I. So this must be inside the radical. So this is just these are primes that would contain the radical. So this is just M. Okay. So this is therefore support of support of R mod I. So remember, we have this inclusion. There's only a singleton element here, which means it is its own minimal. So here is, and this is also equal to n. Because this is singleton, so that is the unique minimal element, and all of these are equal. And that says that I is M primary. Okay, so these are some general remarks about M primary ideals. So now we would like to understand. So let's step back and look for a minute. What have we proved? Okay, so we show. So context is R is Noetherian, M finitely generated, and n inside M. Okay. We introduced the notion of an associated prime. Okay. What does it mean to say it's an associated prime? A prime is associated to M, prime is associated to M mod n, etc. We also introduced the notion of primary submodules. What does it mean to say M mod n is primary? And what does it mean to say it is P primary? And we also got a primary decomposition. Okay. So far, let me just summarize. We know what notion of associated primes is. We know what primary submodules are. I mean, at least I shouldn't say we know, but we actually have seen them. And also, we know that there is a primary decomposition. So this just means that there is a decomposition in which each factor is primary, so they have a unique associated prime. Okay, but what about the associated primes of M mod n for our, if it is not primary? Okay, so here is the proposition. R Noetherian, M finitely generated, n inside M. Okay. Let n I equals 1 through some M be an irredundant primary decomposition. Okay. So that is, so each of these is primary. So in other words, the radical of the annihilator of M mod Mi is a prime ideal. This is a prime ideal, and Mi is primary for this prime. Okay. And this is different from the corresponding prime for a different ideal, for all I different from J. This we saw. Given a irreducible decomposition, we can combine the irreducibles are primary, so we can combine the reducible factors corresponding to the same associated prime and rewrite them, and such a thing would be an irredundant primary decomposition. That's irredundant means this. Redundant primary decomposition. Okay. So then the associated primes of M mod n, okay, is equal to the set of associated primes of, which is equal to the annihilator of M mod Mj. Okay. Mi, 1 less than or equal to I less than n. So each of these factors here, M mod Mi, contribute one associated prime and distinct ones, and that's exactly the list of associated primes of n, M mod n. Okay, so this is this proposition. So every associated prime of M mod n gets a contribution from this, and so this is the this is this proposition. So, okay. So we go back to the to a sort of argument that we used earlier. So we have an injective map from M mod n to the direct sum of M mod mi. Okay, so we have R linear injective map. The reason is there is a map from M to each one of these factors, which gives a map from M to the direct sum, and the kernel is the intersection of the mi's, which is n. So this becomes injective. Okay? So this now means that associated prime of M mod n is inside the associated primes of the direct sum. Okay? But these are themselves primary, so this is just exactly the annihilator of M mod mi, the radical of the annihilator of M mod mi. Okay? And this is a direct sum of modules, therefore the associated primes one can just take the union. So from each factor in the union, one gets exactly one mod. So this is okay. So the associated primes of M mod n is a subset of the associated primes on this side. Okay. So this is just the easier direction, a slightly easier direction. Okay. Now conversely, so let's write. So let's look at intersection of mi over n. So this intersection, I different from j. Okay. So call this module Wj. Okay. Now each mi is inside mi and they contain n. So mi mod ni is inside M mod n. Okay. And the intersection is also therefore inside M mod n. Okay. And because this decomposition is irredundant, we can't really remove any of them. If you remove any one of them, we will not get n. Okay, so this is really not zero. Okay. This is a non-zero module. That's the. Okay, we have skipped the jth one, and that we call Wj, and it is inside M mod n. Okay, and now from M mod n to the usual map, direct sum of M mod mk, k goes from 1 to m. So if you take this map and look at where this lands, okay, so let's take a look at this thing. So elements here belong to mi mod n for I different from j. So in this factor to a k different from j, it gets killed. Okay. So image of Wj inside M mod mk is 0 unless k equals j. Okay. This is also injective. Okay. So image of mi over n, intersection of this in M mod mk, this is I different from j, is 0 if k is different from j. Okay, so that's the observation that we have to make, and hence Wj will go. So this is Wj. Okay, so hence Wj, because Wj to this map has to be injective, onto the jth factor here it has to be injective. Therefore, Wj injects into M mod mj. Okay. In other words, associated primes of Wj is equal to this associated, the annihilator, the radical of the annihilator of this one. So this is, again, this is a primary ideal, and its radical of the annihilator is some prime ideal, therefore, and it is primary to that prime ideal. Okay, but what does that say? So it says that, but the associated prime of Wj is the associated prime of the jth factor here, but Wj also sits inside M mod n. We conclude that the radical of the annihilator of M mod Mj is associated to M mod n. Okay. So this tells us that not only does a submod, so this is the end of the proof. Okay. So this proposition tells us that not only do we have a primary decomposition, decomposition into primary submodules as an intersection of primary submodules, one also gets that the associated primes corresponding to the primary submodules, that's exactly the list of associated primes of M mod n, and in the redundant case, they occur exactly once. If there are M terms here, n has M associated, distinct associated primes. So now we would like to discuss a little bit more about, so this is one property of the primary decomposition that we have. Okay. We would like to discuss another uniqueness property, so which is proposition. So now we will restrict ourselves to rings and ideals and not work in the generality of modules. It is not. It's a little easier to visualize this picture than the one for modules, although the proof is essentially the same, but we will restrict ourselves to. Okay. So R Noetherian, okay. I is an ideal, I ideal. Okay. So now then with primary decomposition, irredundant primary decomposition, decomposition I as an intersection of ji's, I goes from 1 to n. Okay. So all the j's are strictly bigger than I. They are R mod ji's have distinct associated primes. They are primary and distinct associated primes. And we saw in the previous proposition that associated primes of I is the union of the associated primes of these, the sets of associated primes of these individual components. Okay. Let Pi be the radical of R mod annihilator of Ji. Okay. The Ji is a primary ideal, so the radical of Ji is a prime ideal, and okay, this is what we have. So this is then M. Let P1, P2 through PR be the set of minimal primes of M, of R mod I. Okay. So we have observed earlier that the minimal primes are associated, so it will show up in the primary decomposition. So let this exactly be the set of prime ideals of R, R mod I, minimal prime ideals of R mod I. Okay. Then for all 1 less than or equal to I less than or equal to R, so for the minimal components associated to the minimal primes, Ji is I localized at Pi and then contracted back to R. Okay. It's uniquely determined. Okay. So this is what this proposition says. So if you have a primary decomposition, so first of all, there is an analogous statement for modules which we omit because it is this statement is a little bit more clear. If you, here's an ideal and it has an intersection, so we write it as an intersection irredundant primary decomposition. Now just look at the components corresponding to the minimal primes, they are uniquely determined. That's what this, okay, it is extend this ideal to localization and contract back. Okay. Okay, so this is what we have, okay, proof. So let's look at, let's extend I to R localized at P. Now this is the same, so what is, let's fix some I in this range where it corresponds to a minimal prime and write P for Pi. Okay. So we want to show that Ji is I R localized at P to contracted back to R. That's what we want to show. Okay. So now one can the following one can check the following, which is I extended to RP. Okay. For J different from I, Ji extended to Rp is all of Rp. Why is that? So remember P is a minimal prime, and Ji for this property means that its radical will contain an element which is not inside P. Therefore, it will contain an element which is not inside P, because complement of P is multiplicatively closed, and therefore when you invert the complement of P, something inside Ji would get inverted and it will become the whole ring. Okay, so this is, so using this one can check that Ji R localized at P is exactly I R localized at P. Okay, so now when we contract it back, we might get a bigger ideal. So let J prime be I R localized at P contracted to R, which is also J R P contracted to R. Now, because of this, so this in principle this could be bigger than Ji. Okay. So now, but what about these? What kills this J prime? So notice that we have J prime over Ji to R mod Ji to R mod J prime to 0. We have this. Okay. Now localize this at P. Localize. Okay. So first of all, what do we know? What are the associated primes of this? Associated primes of this is just P. Okay, so here associated primes is just P, which means that associated prime, so from this we get that associated primes is also just P, which means that's okay, so we want to prove that J is equal to J prime, Ji is equal to J prime. All of this argument is necessary if it is not equal. Okay. If Ji is not equal to J prime, then do this. Okay. So then this is a non-zero module and it has an associated prime and we localized it P. So now what? Okay. So this now implies that J prime mod Ji localized at P is non-zero because associated primes are inside the support. So this local is non-zero. But on the other hand, we get, okay, so on the other hand we get from the exact sequence we get J prime mod Ji localized at P to Rp Ji are localized at P to Rp, J prime are localized at P to 0. But these two ideals are equal. They may be different in R, but once you invert element outside P, they become equal, which means that the surjective map is actually also injective. So this is also injective, which is a contradiction. Since which is a contradiction if you assume that J prime is, since J prime mod Ji localized at P is not 0. Okay. So that proves that the minimal components are uniquely determined. Okay. The primary component corresponding to the minimal primes are uniquely determined. Just one definition which we should, we say that P in associated prime, we just move elements of associated primes of M, which are not in the minimal primes of M, are called embedded associated primes. Okay. So in the example that we had seen earlier, okay, in the ideal x square times x square comma x times y, this is x intersect x squared y. Okay. This is a minimal, so minimal of R mod I, this is the previous example, is just this prime, while associated primes are the prime ideal x and the prime ideal xy. Okay, and this is an embedded prime. So we'll end this lecture now, and in the next lecture we will look at a few more properties and some examples.